Let's look at a few more examples of using implicit differentiation. So to start out with, let's find the slope of the tangent line to this crazy graph at the point 0, 0. You can see that 0, 0 is on the graph of this equation. Definitely we aren't going to be able to solve this equation for either x or y, so we can't find this derivative explicitly. We really are forced to use implicit differentiation here. So taking the derivative on both sides of this equation, right here we have to use the product rule, and any term that has a y in it, be careful about using the chain rule so that y prime shows up. So we need to do the product rule, so we get 3x squared, derivative of the first one, times the second one, y, plus x cubed times the derivative of y, which is y prime. And now for this term we have to use the product rule again, so minus 3 times derivative of x is 1 times y cubed minus 3x times the derivative of y, which is 3y squared y prime, right? Remember, when we take the derivative of y cubed, we have to use the chain rule because y is a function of x, so this is a composition. So here's the derivative of the outside with the inside in it, and then there's the derivative of the inside. All right, now derivative of minus x, that's minus 1. Derivative of plus y squared, that's 2y y prime. Again, don't forget about the chain rule. And then derivative of minus 2y is minus 2y prime. So all of that equals 0. Now, ultimately, right, we need a value for y prime. Since we're looking for the slope of a tangent line, we could solve this equation for y prime. But we have this point in mind, 0, 0. So we could either do all the algebra to solve for y prime and then plug in 0, 0, or we could plug in 0, 0 right now. Remember, if you have a particular value in mind, you can't plug that in before you differentiate, but right after you differentiate, you can plug in these values. So we've taken our derivative, so now we can plug in our point 0, 0. And that's going to make this way easier because most of these terms disappear. So we get 0 plus 0 minus 0 minus 0 minus 1 plus 0 minus 2y prime. Right, so plugging in our point before we do all the algebra is much nicer, right? Because we're left with this, minus 1. And this derivative is at the point 0, 0. All right, so now we can solve for the derivative. So move the 1 over, divide by minus 2. We get that y prime at 0, 0 is minus 1/2. And that looks about right on the graph. You know, the slope of the tangent line there looks like it's about minus 1/2. All right, for a second example, let's find the points on the graph of this thing, which has this equation, where the tangent line is horizontal. So it looks from the graph, it seems pretty clear that there are going to be 4 places that we're talking about, here, 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 and here, but it's hard to tell exactly where they are, right? In fact, maybe the x-coordinate of these points is plus or minus 2, but maybe it's not quite exactly plus or minus 2. It's hard to tell. By the way, you might recognize this graph if you've worked with polar coordinates before. This is a graph of a polar function called a lemniscate. But anyway, so to find places where the tangent line is horizontal, well, we'd better find the slope of a tangent line. So we need to find y prime. And to find y prime, of course, we have to use implicit differentiation because there's no way we're going to be able to solve this for y. So let's take a derivative with respect to x. So in this first piece, you know, maybe it's going to be easier if we multiply out this left-hand side first. So let's do that. We get 2x to the 4th plus 4x squared y squared plus 2y to the 4th. And then on the right-hand side, 25x squared minus 25y squared. Okay, now I have doubts that multiplying it out was the right thing to do, but it'll work either way. Okay, so now let's take a derivative on both sides with respect to x. We get 8x cubed plus, now we have to do a product rule, so taking the derivative of the first part, we get 8xy squared plus, and now derivative of the second part, 8x squared y times y prime. Don't forget about the chain rule. Now derivative of this part plus 8y cubed times y prime. All right, and then on the right hand side, 50x minus 50y y prime. Okay, now we need to rearrange this to get all the terms with y prime on one side and all the terms that don't have a y prime on the other side. So 8x squared y prime plus 8y cubed y prime, and then this term needs to come over, so plus 50y y prime equals, now these two terms have to go over, so 50x minus 8x cubed plus 8xy squared. All right, now on the left-hand side, we need to factor out a y prime, so 8x squared y plus 8y cubed plus 50y, all times y prime, equals 50x minus 8x cubed plus 8xy squared. All right, and now divide to get y prime. So we get y prime is 50x minus 8x cubed plus 8xy squared over 8x squared y plus 8y cubed plus 50y. Okay, so finally we got y prime. So what were we looking for? We wanted to know where's the tangent line horizontal, but this is going to be where the slope of the tangent line is 0. Well, here's the slope of the tangent line. If we want to know where this is 0, we can just set this equal to 0 and solve. When we do that, the first thing we can do is just clear the denominators, right? Multiply both sides by this entire denominator. On the right-hand side, it just gets eaten up by the 0. So that leaves us with the equation 50x minus 8x cubed plus 8xy squared equals 0. So this gives us this equation that, so we're looking for points that satisfy this equation. So for one thing, we can factor out an x. X times 50 minus 8x squared plus 8y squared equals 0. Okay, and this will have two solutions, or two, right? We can use the zero product property. Either x is going to be equal to 0, or 50 minus 8x squared plus 8y squared equals 0. But x equals 0, that's sort of an extraneous solution. This isn't one of the points we're looking for, because if you look at the original graph, the only point on the graph where x is 0 is this one, and that definitely doesn't have a horizontal tangent line. The reason that this is showing up when we solve this equation is because this graph sort of has two tangent lines at this point, one that's going up and one that's going down, and that kind of makes the derivative formula confused, essentially, right? What's really happening here is at the origin, it's actually invalid to use implicit differentiation at the origin, because at the origin, near the origin, y is not a function of x, right? Because there's this crossing that's happening. As long as you're away from the origin, right, there is some neighborhood near the point where y is a function of x, but that isn't true at the origin. So we have to actually discard the origin. That leaves us with this. So let's solve this equation. Minus 8x squared plus 8y squared equals minus 50. I'm going to get, let me divide both sides by negative 8 here. So x squared minus y squared equals, let's see, 50 over 8. So that's 25 over 4. And this doesn't give us just a single solution. So we have this equation where we're insisting that the slope of the tangent line be 0, and we get this whole graph's worth of solutions. But what we haven't done is we haven't added the condition that we're looking for points on the original graph. So this is one equation that we're trying to solve, but we need to simultaneously solve this equation up here. So 2x squared plus y squared squared equals 25x squared minus y squared. Okay, is that the whole thing? Yes. Yes. Okay. All right. So we know that x squared minus y squared is 25 over 4, so we can plug that in right now. So 2 times x squared plus y squared squared equals 25 times 25 over 4. So we get x squared plus y squared squared is 25 squared over 8. I moved this 2 to the other side. All right, now when we take square roots, we get x squared plus y squared equals 25 over 2 root 2. Square root of 8 is 2 root 2. All right, so now we have these two equations. And we can solve these equations, right? So if we add these two equations together, what we get is 2x squared. The y squareds cancel. We get 25 over 4 plus 25 over 2 root 2. Now we can divide both sides by 2, so x squared is 25 over 8 plus 25 over 4 root 2. Maybe it would be, to put these two fractions together, maybe it would be a good idea to rationalize this denominator. So this is 25 over 8 plus 25 root 2 over 8. So this is 25 plus 25 root 2 over 8. That's x squared. And now we can find x. So take another square root. X is plus or minus the square root of this whole mess, 25 plus 25 root 2 over 8. Now that we've found x, we can go back to the original equation to find y if we wanted to, and that would give us these points here, 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 and here. So it looks like, right, this is not going to be 2. So looks like these points, we could get a decimal approximation, but they actually are a little bit out past 2. For a final example of what we can do with implicit differentiation, let's take this curve and let's find an expression for its second derivative. Well, we can use implicit differentiation to find a first derivative, no problem. So take a derivative, we get y prime cosine x minus y sine x. That's using the product rule on the left-hand side. On the right-hand side, we get 2xy squared plus 2x squared y prime. That's using the product rule on the right-hand side. Now we can rearrange this to get y prime. So y prime cosine x. I'm going to move this term with y prime to the left. So minus 2x squared y prime. Move this term without a y prime to the right. 2xy squared plus y sine x. Now factor out our y and divide. So factor out the y prime and divide. Y prime equals 2x y squared plus y sine x over cosine x minus 2x squared y. All right, so this is y prime. Well, if we're looking for y double prime, I guess what we need to do is just differentiate again. So y prime is going to be the derivative of this whole mess. Okay. Now, in principle, this isn't difficult. In detail, of course, we have to be really careful about the quotient rule and the chain rule as we take this derivative. So to take a derivative of this, we get derivative of the numerator, which we have to use the product rule and the chain rule, so be careful, 2y squared plus 4x y prime, that's the derivative of this piece, plus y prime sine x plus y cosine x, that's the derivative of this piece. So all of that times the denominator, cosine x minus 2x squared y. So that's the first piece of the numerator of the quotient rule. Oops, I deleted a y. So now minus the next piece of the numerator of the quotient rule, that's the numerator with no derivatives, so 2xy squared plus y sine x. So that times the derivative of the denominator. So that's going to be minus sine x. And then we have to do a product rule. 4xy minus 2xy prime. Okay, so all of that over the denominator squared. Cosine x minus 2x squared y all squared. Now, we have a bunch of y primes showing up here. Here. But remember, we have a formula for y prime. So to finish off, all we would do is take our formula for y prime and stick it into all of these places. Now, of course, that's going to make a giant mess. So I won't write out what we get, but you can see that in principle, what we've calculated, this is second derivative, what we've calculated is the second derivative of y, and the formula that we're getting here is a function only of x and y. So just like we did with y prime, we got a formula involving x and y. We were able to get the same thing for y prime, a big, very messy formula for y prime that only has x's and y's in it.